Okay, hello everybody, this is Germán Garcia. This is the fourth lecture in time series analysis, codename MMA 702. Today we're going to be talking about conditional heteroscedastic models and why such complicated word is actually pretty important. So, main application of this is volatility of assets. Okay, the value of assets, as we've said in previous lectures, cannot be completely determined by our models. And so we have to talk about volatility. What we're going to use? What is the volatility for us? Volatility is the conditional standard deviation of the asset return in price. Why is this important? Well, it has very important applications. The most important of them would be derivative pricing, for example, with the Black-Scholes formula or some other ones, and also risk management, value at risk, and interval forecasts. A key characteristic for volatility is that it, as I said, is not directly observable. So we have to model it somehow and play with it. So first of all, how can we calculate this? There are different versions of sample volatility, but the one we're going to be using mostly in this course, the one we're going to be using at all is conditional standard deviation. The reason why it is pretty practical, it's also relatively simple to use in comparison to others. And so if you go to French, Svert and Stambach, section 315, there's an interesting use of high frequency data there. Using, if you're playing with the ranges instead of prices, when we call range to the difference between the daily high and the daily low price, there's some interesting properties there with low returns. So our focus here in this course is mainly on the econometric side of things. So that's what we're going to be, what we're going to be talking about first. So this is figure 1, time plot of the daily VIX index from January 2 to April 6, 2017. Now, there is one important thing to consider always, and it's volatility is mostly annualized because economic forecasts are usually done on a yearly basis. Analyzing of volatility is very easy to do as long as you take the data frequency properly. For example, if you use daily returns in econometric modeling, the annualized volatility is defined in this way, using this square root. And here sigma sub t is estimated volatility. And if you use monthly return, annualized volatility is this value over here. Here you have the square root of 12 months, basically. Our discussion, however, we're not going to be used annualized volatility because that's something we already know we can use by just changing the time frequency, but we will be using our regular sigma sub t, regular estimated volatility. So econometric modeling parts from a hypothesis, and is that the shocks, the unpredictable part of asset returns, are not serially correlated, but they are dependent. There are some dependence relations there. This implies that serial dependence, if there is any, it is nonlinear. It will be shown by the autocorrelation factors of returns and absolute returns of some assets that this is indeed the case. So for basic idea, this is the basic structure of a volatility model. Here the return is the mean plus some shock value, and this mean is determined, well, in this way. We have seen it. We have seen it in previous lectures. This is actually a linear model, but volatility models are concerned with time evolution, not of R sub t, but of the variance of R sub t. If we consider all realizations until time t minus 1, then we are talking about the variance of R sub t condition throughout this. I mean, the conditional variance. This is a subindex, by the way. This is a subindex. For example, we're going to consider the closing index of Standard & Poor's 500 for January 3, 2007 to April 6, 2017. The returns follow approximately an MA2 model with this coefficient here. Conditional variance is very slow, so residuals show no strong zero correlations. I'm not going to do the R demonstration for this one, but I will upload the R file to Canvas directly, so you can take a look at it very quickly. Now, this is the plot of the residuals, and this plot comes to show a very interesting property, and it's that volatility is not constant over time. Here you see big cluster, here you see another big cluster. This is referred to as volatility clustering. We will see some of that a bit later on. This is the sample correlation functions for the square residuals with the model we have used previously. And so how do we model the evolving volatility? Well, autocorrelation function of the square residuals, always. This is already a bit more regular than well, just using residuals. So in volatility models, there are two general categories. In one of them, we use a fixed function, and the other one, the conditional version, we use a stochastic function of the available information. And I mean, if you go here, this is a stochastic equation. And so we will mostly be working with univariate volatility models. These are the most common ones. Well, these are basically every popular one there is. But basically here is our base model, ARCH, are initials for autoregressive conditional heteroscedastic model. It was made by Engel in 1982, and there are different variations. Some of them will be seeing, some of them we'll see in future lectures. But most important ones are generalized arts by Boleslav. I don't remember what the I stands for now, but they're well. IG art is a very important one. Exponential is a really important one, and then there are different measures: threshold arts, asymmetric power arts, and so this is such a general model that it admits a ton of variations depending on what you want to do with it, mostly. So this is an arch model. We're going to model our shocks by the product of conditional standard deviation and a sequence of identical, independent and identically distributed random variables within zero and variance 1, called epsilon sub t here. The coefficients alpha are alpha 0 is greater than 0, and alpha sub y, these ones, are greater or equal than 0 for all i's greater than 0. What we're doing here is basically building our variance as a linear combination of variances in some sorts plus a fixed coefficient. Okay, distribution of the epsilon sub t is not trivial. Here we will see two types of them: normally distributed, and student t distributed. They have a really interesting mechanic within them. So we're going to see, as we did with the AR model, we're going to consider arch models starting from the smallest version with just one coefficient. We will call that arch1. The equation has its form. And so it has interesting properties. The first one is expectation is 0. The variance is given in this way. If you remember correctly, this is exactly the same as we had in an ARS model, in an AR model. If and only if, of course, alpha 1 is between 0 and 1, and it's not any of them. And under normality condition, this is extremely important. This M4 stands for the fourth momentum, aka kurtosis. And so, if this third property implies heavy tails, one thing we can be absolutely sure of is that this is greater or equal than 3, and that's why it implies heavy tails. However, this is conditioned to alpha 1 squared being upper bounded by 1/3. So it has interesting advantages. It's very simple. It generates clustering, not volatility, and it has heavy tails because of this high kurtosis. But distribution is symmetric, which is not very good if we want to use it to forecast. It's very restrictive. I mean, it's extremely simple. It provides no explanation around the data. I mean, it's basically the simplest model we can build with that. And predictions are not that good if you introduce different steps. So, first of all, when building an arts model, we have to model the effect of the mean in this model, which is called arts effect. So null hypothesis, no arts effects, alternative hypothesis, arts effects, and in order to do that, we will go for square residuals and test for Q statistics. I mean, McLeod-Lee, Engel, we can use the Young box test as well. In order to determine the order, we will use partial correlation functions of the square residuals. In theory, in practice, we will look for a reasonable order. It could be 5, 7, depends on how many coefficients we will be using. For estimations, we will use maximum likelihood estimates or quasi-maximum likelihood estimates. And finally, in order to check the integrity of our model, we will use Young-box Q statistic of standardized residuals and the square residuals as well, and skewness and kurtosis, because we already know something about that. R provides a lot of plots for model checking, result presentation. There are many tools for that. In order to work with that, we use package FGArch. There are others, but FGArch is definitely the most complete one and the one I recommend you to use. Spatial model. In order to estimate volatility models, we can use garchfit command. The program is easy to use and it allows for several types of innovation and distributions. And these innovation and distributions are the epsilon sub t coefficient we've been considering. Its occurrence of that is called innovation. And so the distributions regular, I mean, the default one is normal, but we can use student t distributions, error distributions, skew normal distributions, skew student t, skew generalist error, etc. There are plenty. Really, we'll be focusing on these two first. And so, except for the inverse normal distribution, other distributions are discussed in the textbook. So you might as well check those one there because the textbook is incredibly comprehensive. Of course, equations of these curves, properties, and everything are also provided. You can just go there and take a look. For an example, there is I have an R file that I'll post for you. For some reasons, I seem to be unable to capture the R window with the streaming software I'm using, so it's getting a bit complicated. But yeah, I will give you I will upload an R file with a demonstration of how this package works. So for our fitted RH1 model, we can write it like this. And the model taking statistics indicate that there are some higher order dependence in the volatility. You go for coefficient Q15 for the square standard results. It turns out that the generalized arch 101 fares better for the data, but what is that? Well, this is the plot for standardized residuals. And what is, oh yeah, generalized arch model, you should check up in the textbook. Now, I was missing a slide for some reason. Now, I will upload another example for this, but now I'm going to consider student T in innovations. Instead of the innovations following a normal distribution, we're going to have them follow a normal distribution with 5.99 degrees of freedom. There's an explanation for this, and it's because the degrees of freedom have to be estimated beforehand, and the result is 599. So, in order to compare with a normal distributed innovation, a heavy tail distribution like student T reduces the arch effect because arch curve is already heavy tail. And the difference between, however, for this example I'll give you there, the difference between the models is actually pretty small. So you can go for whichever fits the most, but generally either normal or student T works fine. Now, generalized arch model. This is the slide I was looking for actually. In this model we're going to be using, instead of only a linear combination of 80 squared, we're going to introduce past variances in our model. Here, the innovations, these epsilon sub t's, are defined in the same way: independent, identically distributed, alpha 0 is positive, alpha y and b sub j are either 0 or positive, and alpha y plus the corresponding beta y is smaller than 1. This is pretty important. We can reparameterize this, and it's one of the reasons why. I'm going to have eta sub t be 80 squared minus sigma t squared, with this being an uncorrelated series. It's not too much for a demanding hypothesis, so we can actually ask for it there. And our model actually becomes pretty interesting because 80 squared becomes alpha 0 as this sum of the 80 minus y squared, and then eta sub t minus a linear combination of eta sub t minus j. Why is this interesting? Because it has the form of an ARMA model for a sub t. This is why we have gone all the way back from generalized arch model to ARMA model. That is going to help us a lot with properties, moment equations, forecasting. Everything works the same as it does in an ARMA model. Now, in order to see this, we're going to focus on the GARCH 1-1, where the 1 is for the length of this sum, and 1 is for the length of this sum. For example, the ARMA 2-2, we have here alpha 1, 80 minus 1 squared, plus alpha 2, 80 minus 2 squared, and beta 1, sigma t minus 1 squared, plus beta 2, sigma t minus 2 squared. That's how it works. It's weakly stationary if alpha 1, beta 1, alpha 1 is positive, beta 1 is smaller or equal to 1, and there is sum less than 1. The model is weakly stationary. Regarding heavy tails, this nice quadratic condition here means that this quotient between between moments, which is mostly kurtosis, is greater than 3. I mean, we have heavy tails. If this is true, we have heavy tails. For the one step ahead forecast, we have an explicit form. For multi-step ahead forecast, we're going to write a sub t like this. And so we can rewrite the model in this way. You may wonder why. The reason why is because it's easier to generalize. And in order to see that, we're going to go to two-step ahead volatility forecast here. And in general, we can go all the way to here. And this is insane because this multi-step volatility forecast is the same that ARMA 1.1 model give us. If together with this B, we put alpha 1 plus beta 1 in place of that coefficient in the ARMA model. So this is huge, really. Now, for example, we're going to go with monthly excess returns of Standard & Poor's 500 index from 1926 for 792 observations. We'll fit this to an AR model. It has a really nice sample variation, really. For Gartz effects, we're going to try to fit this into a Gartz 1.1 model. And we get this coefficient. There's a tool in R to do that. Implied and conditional variance is still pretty small. I mean, it's not quite the same, but it's super small. I mean, the difference is 10 to the power of minus 4. So the difference is extremely small, actually. So the AR coefficients are statistically insignificant, we can say. So for a simplified model, we can go this way, from here. You may be wondering why. The reason why is because if the coefficients are statistically insignificant, you can drop them from the model and work with something smaller. And so we go here. For model checking, for residuals, we have nice values here. And for square residual, we have nicer values here, really. Now for forecast, we have the following one step ahead forecast, which can be written in this way. And so here we have the corresponding horizon, the return we're getting, and the volatility. I will upload another R file with this demonstration, so you can follow it. I mean, with this model. Now, we have been talking about normal innovation, but now we're going to talk about student T innovation. Sometimes one will work and the other one won't. The reason is because student T has heavy tails. And so for the estimation of degrees of freedom, we have roughly 7 degrees of freedom. And so we have the following model. Evaluating this forecast is not easy. And you can check this reference by Anderson and Boleslav in order to find more details. Like student T actually makes things a bit more complicated. Now, now I'm going to turn an eye to eGARTS models. The smallest one is called the eGARTS 1.1 because this sum has one parameter. This sum has one summand as well. And if you look here, the difference mostly is this used to be alpha 1 with the condition that it's summed less than 1. But here we want alpha 1 plus beta 1 exactly equal to 1. And so we can replace alpha 1 and subsequent alpha sub y with 1 minus beta sub y. And so we have this model here. For the monthly excess returns of the Standard & Poor's 500 index, we have this nice model here, and our L step ahead forecast, we have this, where H is the origin time, we could say. What we see here, why this is important? This is important because the effect of this, the effect of the first iteration is persistent, and so if you look it this way, this is constant, this is a number, and so this is basically the equation of a straight line, where the slope is actually alpha zero. If you plot variance versus variance returns versus number of steps, the volatility forecasts are a straight line. Okay, this is big. Of course, there is an exception. The exceptional case is when alpha zero equals zero, when the volatility forecast is a straight line. Not a straight line, a horizontal line. So the volatility forecast becomes a constant. And well, this might not sound very useful, but it's widely used in risk metrics to talk about the value at risk. So I have an example here of an eGARDS 1.1 model for this data. I will upload this. It should be up on Tuesday morning. So yeah, together with this one, I'm very sorry about the other examples here, but I'm not being able to record them properly. So what I'm going to do is upload the corresponding codes, so you can actually follow those that you may be interested in. And well, this is the plot with excess returns and fitted volatility. Well, it seems to fit. It seems to fit pretty nice, right? So this was basically it for lecture 4. I will see you. I will see you on Wednesday to talk about lecture 2 and 3. General troubleshooting like the other time. This lecture will be up Tuesday morning. Lecture 5 will be up Wednesday morning after a meeting. And so I hope to see you all there. Have a nice weekend.